Just know I'm not an expert by any means at all. I did try doing these solutions on Saturday morning. I did solutions to like 2.5 past papers, so everything's a bit of a blur, but I did send them to Alex and he did review most of the questions. So these are my revised solutions. I also did have a chat to Liz about the first question they were about to do earlier today, but we'll get to that when we actually do it. She kind of helped me out a little bit, and I can show you like the working. Does anyone have any questions before we start?
Yeah, how are we on like a first name basis with these teachers? How like us crazy?
With who?
All of them. Like, oh yeah, I got one.
No. Okay. The first paper we're doing is 2020. So if you guys want to, I'm not going to show the questions. I'm just going to go straight through solutions. So if you guys want to see the questions, you have to get them up yourselves. Sorry. And also 2020 was a year that I think they either got to take it home or it was open book and the exam was open for like a couple hours or something. So it is kind of hard or harder than what everyone is kind of expecting for this year. I'll tell you what Liz told me because I just chatted with her. Liz said that the best way to practice for her half of the exam, other than just reviewing all the content and being like aware of what all the topics are and like understanding them, the best way to practice for them is to do the midterm practice questions and review the midterm, because the questions are going to be similar in style to those. I don't know if everyone was here for that lecture, but she did say that we do need to know how to construct integrals. So I have a feeling it's going to be kind of similar to that question where, you know, in the midterm, I think question 2, where it was like a sphere and you need to construct a spherical integral for like a little area on the sphere. Anyway, that's okay. I think that's going to be in the exam. Also, Oleg said that he's not going to copy paste one of the assignment questions, but he is going to make one similar. If you look at some of the past papers on Oleg's website, you'll see that there's circuit questions in his last 2 exams that he's written. So I think it'll be either a circuit question or the toroid question might come up. In the past papers that I've seen 2 toroid questions, but I can't remember if Oleg wrote the one from 2015. So I don't know. That's my guess. Toroid question and the circuit question. But I've also seen him do a lot of polarization questions, which we'll do today. So yes, before we jump into this, know that this one is going to be a hard exam, but it's still good to see the working and the techniques that we can use to solve the questions. Is everyone all good to get started? Oh, let me just go to 2020. Okay, so question 1 talks about an infinitely long dielectric cylinder of radius r with an axis of symmetry along the z-axis. That's a pretty usual setup. It has a frozen-in fixed polarization, and I'll just write that down. So this is 20. That's going to be really small, isn't it? Yeah, okay. And this is question 1. A. We know that, whoa, disappear, good. We know that they give us P is equal to P naught in the x direction. Cool. And P naught is a constant, sweet as. Question A asks us to find the surface and volume-bound charge density for the cylinder, and it's only worth 2 marks. Let me just switch right on over. Hopefully you guys write this down on your formula sheet or just remember what it was, but the surface-bound charge density is expressed like this. Do people remember seeing that in lectures or just like feel comfortable seeing that? Is that also big enough for people? Love it. Okay. So the first thing we're going to want to do is evaluate this. Just so you guys remember, this upside down triangle, I never remember the names, is, maybe it's called del, I can't remember. We want to find essentially the derivatives of all the x, y, and z components. Did you guys want to do this question in Cartesian coordinates or in cylindrical? Cylindrical? Okay, cool. I also did this in Cartesian coordinates at first, and I got the first question right, but I got the second question wrong. And then I did it again with cylindrical coordinates, and it's just a lot easier to see it's a lot easier to manage the question in cylindrical coordinates. So I'll just write down what is it called a del operator? Nabla, I'll call it Nabla. I'll just write down Nabla for cylindrical coordinates. And this, I think, is on the portion of the formula sheet that they're going to give to us. So it's 1 on R, and I'm just going to be really careful with my bracket placement here. So this little thing that I've written means I'm going to take the partial D partial R of R, and then you'll see I'm going to multiply something in here. Whoa, that did not. You'll see what I mean in a sec. And then the second component is just 1 on R d phi. And the last one is just your regular old d dz, or partial. And this is a vector, and I'm going to take the dot with that. And does anyone remember how to convert from Cartesian to cylindrical, just off the top of their heads? No, that's okay. Neither did I until I looked at the formula sheet. And it goes a little something like this. So just give me 1 second. How do I explain this? This is equivalent to, and tell me P naught, sorry. P naught cos, oh my gosh, what? Cos phi in the x direction plus P naught, and I'm so sorry because that's actually a minus P naught sine phi in the phi direction. Are people okay with that? Okay, awesome. So that's what it is from Cartesian to cylindrical. I'm just going to input that in here. So that's going to be a P naught cos phi and a negative P naught sine phi, and then a 0. Oh, yes. And yes, sorry. And just for reasons that you'll see later, I'm going to denote that as S. But it's the exact same thing. How do I not be stupid about this? No. How do I move down? Watch this. Oh, clever. So wait, you know how we're allowed to write our own formula sheet? They're also going to give us the formula sheet, and on that formula sheet, I'm pretty sure it's going to be the same as it was in the 2020. Oh, not the 2020. They didn't give it in that year. I think in 2022 was the last time they gave out the formula sheet. Maybe even last year, but we don't have that past paper. And on there, it's got a bunch of things. It has all this stuff on it, so you can convert between them. It also has all of the Nabla identities, and this is one of them, so this will be on there. It also has, sorry? We do get a formula sheet, but we also get to make our own. Yeah. Back to this question. So we have this for our row sub B, and then we're just going to evaluate it. I'll just show you guys because this is kind of important, and in my maths classes, they pointed this out specifically when we did this. So I'm just going to take the dot product of the top thing, and that's going to look like 1 on R d dr. I'm going to open this bracket, and I'm going to do R times P naught cos phi. So I'm taking the partial d partial R of the whole expression, and that's all that one done. And then I'm going to add, and it's going to be a minus 1 on R d phi of negative P sine phi. Does that make sense? Beautiful. And then when I do that, if I take ddr of this expression, this is just the constant, so that's the only thing that gets left. I get negative 1 on R P naught cos phi. And then this one is with respect to the phi, so this is going to go into a cos theta, and the two minuses are going to just end up being a plus. So what we find is that we should just get a big fat 0. All sweet. The next thing that they wanted us to find was the volume charge density, which hopefully you write down on your formula sheet is going to be this, and hopefully you recognize it from lectures, is this one. So it's the polarization vector multiplied by the normal vector. In our case, the normal vector is just the radial vector, so it can be written as sweet. Cool. Doing the same thing as before, I'm going to write out my p vector, and that was p naught cos phi negative p naught sine phi and 0. And I'm going to multiply that by my r hat. My r hat is exactly the same as 1, 0, 0 in cylindrical coordinates. So the only thing I'm going to keep is my top component. Oh my gosh. Stress. So I'm going to get p naught cos phi. Chillin'? Nice. Okay, cool. That is the first question done. And that one was worth 2 marks. Can someone see that? I think that was worth 2 marks. Yeah, kind of annoying because you just have to like remember the formula first of all and then just plug and chug. So yeah, for part B is the electric field inside the cylinder. One thing I want to make super clear is that this is a linear dielectric. That will come into play later. Hopefully you guys remember that for stuff in general, the electric displacement vector is written as this. You guys remember that? Love it. I use that all the time actually, so I guess it's pretty useful. And then another identity that we're going to use is this bad boy. Hopefully you guys have seen that one before and hopefully remember it. What I'm going to do is I'm going to take the nabla of this side, and by doing that I'm going to get, oh, it's not liking me. Nabla of D, my bad, I guess, is equal to nabla outside of, I'm literally just substituting it in. Literal, just straight substitution. When I do that, my epsilon naught is a constant, so I can take it out of my nabla, which is essentially just a derivative in like vector space. So when I do that, I'm going to get this. Also because you can think of it as a derivative in vector space. Derivatives are linear, so you can do this. I'm pretty sure this is something that they might also give us on the formula sheet. Happy chappy. Cool. We know from part A that this PF is 0, so we can chuck that 0 there. And then rearranging, we get, if I chuck the polarization vector onto the right-hand side, I'm going to get E naught. This is equal to negative this. And then hopefully from A as well, we showed that this was equal to 0. So this just becomes this is equal to 0. And we can just chuck the epsilon over onto the other side and we get this is equal to 0. Cool. Now that we've just shown all of those things, we can go back to our original displacement. Yeah.
What was PF 0 again?
In part A. Yeah. Yes. So now we go back to our original electric displacement equation and we get epsilon naught E plus P is equal to 0. There's just a point that I want to make here. When I sent this off to Alex, he said that this equation is not strictly true. I didn't know what he meant by that, but then I asked Liz, and Liz said that this cannot be true for all cases. Like you just said, like if there was free charges flying around, there would be some constant on the right-hand side. Liz said in the context of this question, everything I just did looked fine. So if you guys didn't trust me, then I hope you trust Liz. Yeah. Another comment Alex also made was that we might need a homogeneous solution to the differential equation nabla e = 0. Liz also said, don't worry about it. It's worth like 2 marks. No chance of doing that. So yeah, where we go from here is we rearrange this and we get electric field is equal to negative P on epsilon naught. We already have a, like in the question we get given what P is. So by literally plugging it in, we get, I'm going to chuck the epsilon naught out the front. And I get P naught cos phi. P naught, I'm pretty sure there's a negative, yep. Sine phi. And then 0. And then I'm just going to leave it as that. But do you guys see how I could rewrite that as -1 on epsilon naught P naught cos phi in the S direction minus P naught on epsilon naught sine phi in the Y direction plus 0 in the Z direction? Do you guys see how that's the same thing? You look really concerned, and that's, are you okay?
No, I'm sure face like that.
Okay, cool. But we're chill. Chill?
Wait, you're saying so we're putting cos of y in the x direction,
The S direction.
and then it'd be sine phi in y direction.
Exactly. Exactly. I like to write them in vectors just because, I don't know, I feel like it's easier to interpret. That ends up being a plus.
So why would you have to rewrite?
I don't know, all the solutions that I've ever read in my Griffiths time and in this course in general always splits them up. Oh, sorry, that was rough. I don't know. I always write it in the vector form. I don't know. It's easy for me that way. I think it just makes more sense to me. It's also easier to see which components are where. But anyway, we all good. Awesome. Please tell me if something comes up that's not good as well. If we look at the part C, the third part of this question, it asks for the electric potential within the wire. This is, hang on, is this the part that gets interesting? Okay, this is the part that gets kind of fun. You can do this a couple different ways, and I'll show you how in a second. So we're going to start with our initial P, which is what we had in our spherical coordinates. And then to find the electric field, we're going to use this good old trusty-dusty identity. We love this one, don't we? I love this one. By doing that, again, I'm going to write out what we got for E earlier, and it's going to be P naught on the S direction plus sine phi in the phi direction. Oh, I'm so sorry. In the phi direction. And that is equal to, I'm now going to write out this right-hand side. And this is where my notation is going to be a little bit different. So this is kind of how Oleg likes to write it. He writes his derivatives like this. So a d with a little subscript s. If you've done a maths course, that's also how they do it in the maths courses. And then this one becomes like this. So that little partial d means I'm going to take the partial derivative with respect to that little subscript. And then I dot that with vs, v phi, vz. And I don't know why all these other dots are coming up. Okay, cool. So this is like the differential way of doing it. You can also do this question using the integral v is equal to negative e dot dl. In this case, that would be ds. Do you guys remember that one as well? I don't really like integrals, or I like them less than just dealing with this differential vector stuff. That's just my personal preference. But if you like integrals, I don't know, go for it. Knock yourself out. To do the rest of this question, I'm now going to evaluate the different components. So I have a phi naught on epsilon naught, not phi, p naught on epsilon naught with a negative at the front, cos phi, and I'm going to evaluate that with the s component on my right-hand side. So that's going to be p naught epsilon naught cos phi is equal to negative dv in my s direction with respect to s. And then if I just solve this regularly by doing an integral, I'm going to get that my vs is equal to p naught on epsilon naught cos phi with an s, so that's a times scalar, or not scalar s, it's a variable s, plus a constant that's going to be in terms of phi. Are we chilling with that notation? I'm pretty sure you also see that in first year as well. And now this is a really fun little thing that we get to do. We get to say, for continuity reasons, let's assume that outside our cylinder, the voltage is 0 or the potential is 0. Are people okay with doing that, first of all? Because when I first saw this in the textbook, I was like, no, what, why? Do people kind of get that? If current is flowing through the wire, an infinite wire, and we also have a polarization in this direction, there's not going to be a voltage outside. There'll be a magnetic field, which we can obviously get from right-hand rule, but there's not going to be a voltage. Another similar thing is like if you have a solenoid, wait, no, that's magnetic field outside a solenoid is 0. Do people get that?
Yeah.
Okay, good. I don't have a better way of explaining it, to be honest. But yeah, we can just say that this is equal to 0. Doing the exact same thing, but for my second bit here, I'm going to get a -1 on S dV in my phi direction d phi is equal to P naught epsilon naught sine phi. Oh, that's so rough. I'm going to do 2 steps in one. I'm going to multiply by a -s onto the other side, and I'm going to integrate with respect to phi, which will turn my sine phi into a cos phi, into a negative cos phi. That negative from the cos phi coupled with the negative on my left-hand side is just going to turn into a positive. So you end up getting V in the phi direction is just equal to S. Where did my, oh yeah, sorry, S, because I multiplied over, S P naught on epsilon naught cos phi plus some constant in my S in terms of S. Again, for continuity reasons, we can say that this is just 0. And now we use the electric field in order to find the potential. Remember that potentials are always scalars. So the way I get my final answer is I just sum my scalars. So, oh my gosh. In my S direction plus V in my phi direction plus V in my Z direction. Because I never had anything in my Z, this will always just be 0. And if you add the 2 things that we just got together, we're going to get P naught on epsilon naught. Oh. 2 times cos phi S. Happy chappy. Good. Okay, cool. This next question, actually. 1 second. The next question is, oh, yes. Okay. Okay, the next question asks us to find the electrical potential outside of the thing, the wire, and it gives you that the general solution to the Laplace equation in cylindrical coordinates is that. I don't know if you guys remember, we had a Laplace equation in the practice midterm. And I'm going to be honest, I forgot to ask Liz. Remember in the practice midterm and generally in these Laplace questions when we're solving for potential outside of like funny objects, a lot of the times in lectures we saw like voltage planes set to like some sort of voltages. When you get to the very end of those questions, you normally do like the Fourier trick. So you do some sort of Legendre polynomial, and then in order to find the constants out the front of the general solution, you do the Fourier trick. I forgot to ask Liz whether or not we actually need to know how to do that, because in lectures we never actually did a Fourier transform, and in the solutions to the practice paper, it like doesn't actually do it. It just kind of like waves its hands and says, this is the answer. So I don't do that here, but I probably should have asked and I didn't. Sorry. Love it. Love it. Okay, cool. Back to this. Sorry? Yeah. That sounds like something Oleg would say. It's intuitive. Let me go. Yeah. Okay, so this is something I like to do anytime I get like this Laplace kind of question or a voltage question in general. I always write down the boundary conditions first because they give you the most amount of information. So we know that the voltage at S equals R, we just found it, and some phi is this thing here. So we know that that's equal to P naught epsilon naught, sorry, there's a 2 there, and there's an S cos phi. We also know that, and this is like another condition that we always use, that as S gets really big or as S goes to infinity, the voltage is always 0. And then this is the really annoying part, and this is my least favorite part about these questions. If everyone can look at just like that massive sum, you can see that there's like a cos plus sine term, and then there's another cos plus sine term. So we have 4 terms with 4 different constants at the front. We essentially just want to look at that equation, start plugging in the boundary conditions until we can try and get an equation that fits with our boundary conditions. I'll show you what I mean. Does everyone have it open? Because I really don't want to get the equation up. Does everyone know what equation I'm talking about? So this is 2020. We're currently on question 1, part D. Essentially, at the beginning of the equation, the second term is a B naught ln S term. By looking at our second condition here, we see that S goes to infinity, which means that B naught ln S should go to 0. I'll write that down. So if S goes to infinity, our voltage has to go to 0. So that means that our B naught ln S has to go to 0. The only way that we can do this is if B naught is equal to 0. Oh my gosh. Is if B naught is equal to 0. Are we all good with that? That's essentially what we do for like all of the terms in, or all of the constants in that equation until we find like our final answer. We also know that as S goes to infinity, that the S to the power of K term, that's like the very first variable after the summation sign, that would diverge. So if I did S to the power of infinity, that would be infinity, but we want it to be 0. So that means that we can say that we can just get rid of it, essentially, therefore get rid of it. And we can do that because that summation is the most general formula for the voltage, and we just want to find one specific formula. So that means now we're looking only at the A naught plus the sum of all S to the negative K, CK cos K phi plus DK sine K phi. That's what our equation is looking at. I'll just write that down so it's a little bit easier. Currently we have this S to the negative K, and that's K equals 1 to infinity. There's also an A naught, but I'll show you how to get rid of that in a sec. CK cos K phi plus DK sine K phi. Okay. Again, I'm going to use the fact that at S approaches infinity, my voltage is equal to 0. As I've set S to infinity, this will go to 0. So that means this whole term is accounted for, but I still have this constant A naught out the front. So I can just get rid of that. I can just say A naught is equal to 0. Sweet. Because as S goes to infinity, the whole thing should go to 0. So this whole term goes to 0, but I'm still going to get left with that A naught out the front. So I'm just going to make that equal to 0 just to fix things. This is also kind of a little annoying thing. As you saw in the questions above, the voltage that we calculated was only in terms of cos. Do you guys remember that? It was like P naught on epsilon naught times 2S cos phi. We don't need the sign to be able to express that cos. So we just get rid of it. We just get rid of it. So we get left with an equation for our scenario that says that V S of phi, oh, that is so dodgy. is equal to this C1 cos phi. I also should explain how I got rid of the K at the front. Again, if you notice the voltage that we calculated in part C, that was only in terms of phi. So I got rid of that as well. And that's why this K here turns into a 1. There we go. So now it's just a matter of chucking in what we know. So we know inside, we already calculated the voltage inside. We need to calculate the voltage outside. In order to do that, we also need to take into account the boundary. So that's the first thing that I'm going to take into account. Remember, we also want a continuous voltage as well. That's why I'm considering this boundary. We need to show that the partial here with respect to S at S is equal to R, so this is on the boundary, has to be equal to dV out on ds at S is equal to R. So I'm just showing that the boundary is smooth. Because in part C, we showed that voltage is only in terms of phi and not in terms of K. Yeah. We're literally in this part when we're trying to find this solution, we just look at the boundary conditions and start deleting stuff until we get an equation that fits the boundary conditions. So we're trying to show this. Does anyone want to have a guess how we're going to do this one? Trusty dusty, this one. Oh my gosh. Oh no. No. This is honestly one of my favorite ones because it's just a beautiful thing, isn't it? It's just that. Okay. If I do that, I get, and hopefully you guys remember, or at least fine if I do this. That's what we calculated for electric field. And then we need that at S is equal to R. If we go ahead and do this, we're going to get this bad boy. The negatives will just cancel. And I need cos at S is equal to R, which means I get, oh, that's not a K, that's an R. Hopefully you can see that these causes will cancel. And you'll end up finding that C is equal to P naught R squared on epsilon naught. So we have found our C. Awesome. The next thing we need to do as well is we want to find our V out at S is equal to R. S is equal to R. Because up the top, oh my gosh. Because up, wait. Because we've just shown that, I think we did inside, that we've just gotten the expression for this, and because we've said that it's equal to that one, we have our constant for our V out expression. Can I scroll down?
Yeah.
Okay. So that means that, get rid of that because I actually have nothing. Oh, actually. No, that's wrong. That means I can say that because they have to be equal at that boundary, my V naught, my V out in terms of S and phi is equal to that constant cos phi. And that's different to our inside one because our inside had 2S in the term as well. Are we all sweet? So basically, let me just, oh, we just did that part, that's all sweet. That's all sweet. And then, yeah. Does anyone have any questions on that? Just super quickly, I'll just go through everything we did, just so you guys can see how it all relates. Okay, initially we find surface and volume bound charges, and we use that to find an expression for the electric field. We then use the electric field to find the potential by taking the sum of the s and phi directions. We then use our boundary conditions to get a general formula for our v expression. That's what we all do here. And then we use that in order to find v outside. And we used our E is equal to negative nabla V equation twice. Does that make sense? Cool, cool, cool. The next part of this question is actually a little bit scary, and I actually didn't get all the way through it because I didn't know what to do. Oh, actually, before we do that, we need to find the electric field outside for S is bigger than R. So a lot of electric and potential stuff. Oh, where is my solution? Right here. Super quickly, again, trusty dusty. Oh, that was really off, but that's okay, you get the idea. I'm not gonna write out what that means again. Essentially, you should get to a formula that looks like this. The S direction minus 1 on S dv d phi in the phi direction, and there's gonna be nothing in the Z direction. We end up plugging in our equations for V that we found in one of the parts above, and you end up getting to E naught R squared on S squared epsilon naught cos phi in the S direction plus P naught R squared on S squared epsilon naught sine phi in the phi direction. Are we all sweet with that? It was just doing that process again. If you don't get that, my solutions will eventually be up on the Discord, so just look in there. But it's literally the exact same thing, playing around with E is equal to negative nabla V. There we go. Okay, the next part, part F. This was the part that I didn't actually get to finish. So, and I asked Liz about it, and she said that it's actually kind of hard, and something this hard probably won't be in the exam. So it says, verify that the electric field satisfies the required boundary conditions at the surface of the dielectric cylinder. So when I was doing this question, I was just like, oh, I'm going to use my boundary conditions from before, start plugging stuff in, and show that it's consistent. That's what I did. But it's worth 4 marks. So I kind of thought this is not enough for 4 marks. I talked to Liz early today, and she says that she reckons that the other 2 marks come from showing that, or knowing rather, showing whatever, that, and hopefully you guys remember from lectures, that when you have like a plane of charge, there's a discontinuity in the electric field. So you find the electric field above, the electric field below, and then you take the average. Do you guys remember doing that? That's where the other 2 marks come from, by taking that average or finding an expression for the above and finding an expression for inside the wire and then saying that it's the average. Do you guys remember that? I actually didn't do that because I only found out earlier today, but I guess I will give that a go before I put the solutions up. But that's essentially how you answer or get the 4 marks for this question. All good with that? Cool, cool, cool. Let's move on to the second question. This, I'm going to be honest, I remember doing this in Liz's part, but it was never like a massive thing. But I have seen questions like this come up a bunch in past papers, so I guess we'll just have to wait and see. So we have a long wire of radius A that carries a current I, and it's surrounded by a long hollow cylinder made of a linear magnetic material with magnetic susceptibility chi m. Let me just, this is gonna, oh, maybe I can do this. Oh ho ho. No, I want an outline. Oh, sorry guys. Yeah, you can kind of see that. Now I need 2 more. Where'd that yellow line come from? Yeah, no, we're ditching that idea. Ooh. No, okay. One more time, one more time. Cool. Okay. This inside radius, oh, can you guys? You guys know what I mean. And this is C. And then what if I use highlighter? I don't have that option. It's okay. This part and this part have a magnetic susceptibility of chi sub m. Awesome. The first part of the question asks us to find the surface-bound current density on the inner and outer surfaces of the cylinder. What is the direction of each current relative to I if the material is diamagnetic? So you guys remember that diamagnetic means that the spins or the, what else do you call them? The spins align opposite to the applied magnetic field. Diamagnetic. Or the domains, that's the word. Magnetic. Okay, cool. Let me switch to my solution. Okay. The formulas that we're going to use for this are, I'm just going to write down all the ones that mention everything. So chi m h. H is just the auxiliary field. I actually don't have a good definition for auxiliary field. I kind of just have seen it everywhere all the time, so I just accept it. So if anyone has a good definition for it, please yell, because I would even like to know. Let me just get rid of this. Another thing that we've seen is, I'm pretty sure, and I might be wrong, that this one is called like Gauss's law for a diamagnet or something. Maybe Ampere's law. I honestly can't remember the difference between them. They all just kind of look the same. And we have this. And we also have this. So J is volume and J is surface, K is volume. Cool. Okay, for this one, I'm going to use the integral, and it goes a little something like this. If I write it out, I get h dot dl, or di rather, is equal to I enclosed. The current enclosed in the question tells you is just I. Now we get to do a fun little thing that we did all throughout first year. We get to say, because of the like the circular symmetry, you can chuck the h out the front as a constant and just leave, I'm sorry, this is dl. That is so my bad. I should have picked up on that. My bad. Obviously, I know. Sorry, okay, dl. And technically that should be a vector. Now we just need to find the integral with respect to dl, and it's just going to be the line integral which makes the circle. So this becomes h, I don't even know how that happens. Oh my gosh, okay. H times 2 pi r is equal to I. And that implies that h is equal to I on 2 pi r. And this is within the region B between R between B and C. Cool. Also, we have H. We also want to, I think the question was asking for like magnetization, not magnetization, but essentially we're going to use this formula to get to our answer as well. So if I plug in my H into this formula, I'm going to get M is equal to chi M times this little r. And watch this, it's in the phi direction. Let's think about why. We know that the current is going out of the page, and we are currently in cylindrical coordinates. So if I is coming out of the page, that means our magnetic field is wrapping around. So that means at any like point on the circumference, our magnetic field is in the phi direction. Does that make sense? Excellent. So that's why I have that phi there. And now I want to find the inner density. I actually can't remember what we're even doing anymore. I just look at the maths and do the maths. So if I want to find this is the volume, and this is at B, because we want to find the inner and outer one, I'm going to do MB times N. Not showing up okay. I feel like that's more faint. Anyway, I calculated my expression for M up here, and I make it an MB by changing my R to be a B, and that's in the direction of phi, and I need the normal vector. So the normal vector on my loop is just going to be my radial vector outward. I'm going to denote that as an R. I know in the last one I said it was an S, but that's just because the question said S. I much prefer R. So much more prefer R. Oh my God, oh my God, oh my God. Okay. If I do that now, I want to take the cross product of the phi and the R. So if I take, it's phi times R. If I take phi times R, I get something pointing into the page, and I denote into the page as being my negative Z, and out of the page as being my positive Z. That's also the orientation we used in the last question. So I end up getting a final answer of chi m I on 2 pi b in the negative Z direction. And I can also put that negative out the front and just say it's in the Z direction. So that's that one. Another way also, is everyone comfortable with using right-hand rule? That's okay, because there is a trick. I know that my MB is in the phi direction, and if we write the phi vector as a 3 vector, we get this. And then if we write the R vector in 3 vector form, you get this. And then hopefully you remember from first year, I don't like the way that Oleg does cross products because like it takes too much time to write. Hopefully you remember in first year, you can like delete that row and then take the cross product of that. In that case, it's just 0 for the first component. You then delete this row and take the cross product of that and that, which is again just 0. And then you delete this row and take the cross product of that. And that's how you get a -1. And because you deleted the third row here, it's the Z direction. So that's another way if you're not comfortable using right-hand rule. Just super quickly, actually, I'll leave that there. To explain right-hand rule using this way, your thumb is the first variable that shows up, your pointer is the second variable that shows up, and your middle finger is the direction of the cross product of those two together. I feel like no one actually ever told people that. But anyway, now you know. Another thing that we wanted to calculate was the outer density. So that's denoted as Kc. And we write that the exact same way. We're literally doing the exact same thing. It looks exactly the same this term-wise, except we put a C in the bottom for our radius, and it's again in the phi direction, multiplied by our radial direction. So we get an xm phi on 2 pi c, again in the negative Z direction. All good. No one's crying or yelling, so that's good. That's good. Now switching over to part B. Part B asks us to find the volume bound current density inside the cylinder. And that's worth 2 marks. That was still part A. What have I done? 1 second. K is surface. Wait, no, it's not. No, it's not. No, it's J is surface. Oh my gosh. J is volume, yeah, because IJK. No. Opposite way. Yeah, that's right. Oh, goodness. Also, a really annoying thing as well is in Liz's section, you have the magnetization vector and you also have magnetization per unit volume or whatever. And that's little m and big M, and that also really annoys me. Yeah, but I can distinguish between my small and big p's at least. Oh, it's so annoying. And then in Oleg's part, you have resistivity, which is 1 on omega, which is a rho, which is the exact same as everything else. I hate it so much. Anyway, we're not here to complain. We're here to just roll with the punches. Part B. I can't even remember what I said part B was. Like volume bound current. Awesome. There's yet another formula for that one. Maybe I wrote it down. I honestly can't remember. That's a vector, and it's like this. Cool, cool, cool. Our M is as it was before, so I'm just going to write it with my R. And that was again in my phi direction. I now want to find my nabla of that. If I take, this is going to be easy to see. Do you guys want me to write out the whole cross product, or are you okay if I write out just the answer? Is everyone else okay with that? Okay, good. If I just write out my whole thing, I'm going to get this expression. Because all of my other derivatives are 0. That's also going to be in the phi direction because I preserve my direction. Cool, cool, cool. That's actually all you needed to do for part B. Just that cross product. Yeah. Why did I put that negative there? Yes. Lol, yes. Yes, yes, yes. Cool, cool, cool. And then C. Let me just go back. C was finding the magnetic field where S is the distance from the axis of the wire for all S. So where's my page? Okay. Yes. We also do this in lectures, but we consider regions. So my first region I'm going to consider is this one, the one that's like empty. And in this one, we have this expression. So because I'm between 0 and A, my R is A. And the reason I don't include a susceptibility constant is because this is the part of the wire that doesn't have a susceptibility. It's just like air or whatever. So from this I get this expression that I is equal to J pi S squared. That should also be an A. My bad. And then using this trusty-dusty formula, H dot dl is equal to I enclosed. By using that, from that I get the exact same thing as before, where I get H 2 pi, in this case it'll be A, is equal to I. I have my I up here, so that's equal to J pi A squared. I actually lied to you guys, and I've made a mistake that I always make. I'm going to leave this as a general expression and as an S squared. I'll leave that one there because it's the exact same calculation. And on this side, I'm actually going to get an S squared, and on this side, I get my 2 pi A. And then the thing that I wanted to calculate was my H. So if I just do my thing there, that goes. Okay, let me actually explain this because this happened to me a lot in the very first part of Liz's thing. Remember when we were considering electric fields in like coaxial cables in like Liz's section, and you typically have like, they say this is R or something, or even if you just consider this, they say this is R, but we do Gauss's law in terms of little r. When we do Gauss's law, if we say that Gauss's law is in terms of little r, you'll get an expression in terms of little r on the left-hand side and an expression in terms of big R on the right-hand side, because the big R is related to the charge enclosed. Does that answer your question, or am I explaining something that you're not seeing? It's okay. And I'll also post solutions on Discord. Yeah. Yes. Let me start this question again. Let me start this question again. Okay. PHYS2114. It's just UNSW PHYS2114, yeah. Let me start this question again, and let me move this down.
It's just because like we're doing the surface glue, as we're doing like the inside, if we're taking like half A.
If we're taking a half A.
So for example, if we're looking at current half A, outcome is still dependent on like the total A.
Wait, why are we looking at the current in only half A?
Just as an example. Like if we're looking at that point.
Are we going back to Gauss's law example? Is that what you're talking about in the current in part A? Or are you talking about this?
Why is the HDL between 0 and
let me evaluate that first. So let me just do HDL for some general thing. I feel like this is getting more and more faint, but that's okay.
Just increase the line size.
Good idea. Oh, maybe even more. This will get, oh, much better. I get from this 2 pi.
I understand doing that, but it's like, why are we going to, so sure.
1 second. This is J pi, and this will be, that's for my initial R. I'll do a big R here. So my little r is a variable, and my big R is a constant.
Oh, it's a constant based on.
Yeah, on the A, B, C, whatever. If I go.
So then shouldn't the A be on the right hand side? S be on the left.
Let me just S be on the left, S be on the left. I'll just rewrite the whole thing. So now we're considering just this region. And my J for that I calculate to be I on pi A squared. Hang on. Let me just also do that for the most general case. So this is a pi R squared. And from that, I get I is equal to J pi R squared. So again, that's a variable. When I do my integral for my between 0 and A, my H dot dl is equal to I enclosed. This side will go to become a variable, which I'm going to say is 2 pi little r. And on my right-hand side, I should get a constant, which is my A. So that'll become a J pi A squared. Cool? Good. The thing I wanted to isolate was my H. So when I isolate that, this is going to delete itself. And, wait, no, before I do that, hang on. Yeah. No, I'm okay. Hang on, sorry. That's exactly what I wanted to do, sorry. Let me just see. And then I get H is equal to J A squared on 2R. And then I need to rewrite my J in terms of my other variables. Just give me 1 second to interpret what I've just written. Look, honestly, we might need to come back to this question because I don't know how to explain what I just did. Okay. We'll also take a break and I'll figure it out in the break. But essentially, because we're going to need to use this part for a following part, I'm pretty sure, you should get an answer that looks like this. It's supposed to be a little r, but that's okay. on a squared, and again, it's in the phi direction. And then this is a fun little fact. Inside the wire, m is going to be 0. That's a condition for this kind of stuff that's in the lecture notes that's really, really useful for some questions. But because we know that this expression, hopefully you guys remember that one. In the lecture notes, they display it differently, but I like this way the best because it's got no minuses and it gives us everything. So that goes to 0 inside the while. So we end up getting this is equal to that. And just by plugging in the h that we just found, we get, again, in the phi direction. So yeah, once I figure out what I did in the first part, this is how you do the second part. Love it. Now we need to consider the next region, which is this one. So hang on. Same sort of dealio as above, but because I need to explain it a little bit better, I'm just going to write down what I get. I'll just write down what I have and then we can suss it out. So I get this guy again. Little r is a variable is equal to my I. And then we also know that m is equal to 0. Therefore, my b is equal to my mu naught h. And then I can say, if I plug in the h that I get, my b in terms of s is equal to mu naught I. And then because we're between a and b, I leave this as an s because s is between a and b. Surprise, surprise, again, phi direction. Last region, b between s and c. This is where the fun really starts. I've seen this technique in a couple of past papers, and it's a really good relationship to know. Going back to this one, we can rewrite chi m in terms of, hang on, let me also write this one so I have everything. I can whoopsies. Wait, no, this one. I can rewrite, what can I rewrite? My b naught like this. But let me explain that. How did I do that? I put these together. I'll just make that really clear. I'm going to change my m in here to be this. Yep, that's b. And then if I take out my h, I get mu naught h, 1 plus chi m. And then a really fun little thing is, like, I've never really seen this simplification actually be useful in questions, but this 1 plus chi m times the mu naught is actually what's equal to mu. That's like another cute little thing to remember, but I've never actually seen it be useful in questions. So yeah, essentially we do the exact same thing again, HDL, and you end up getting h outside of 2 pi, we're dealing with s, is equal to I. Ugh. From that, you end up getting that h is equal to I on 2 pi s. And then we want to plug that h back up into this. So we get that b in terms of our s is equal to mu naught I on 2 pi s, 1 plus chi m. And that's all in the phi direction still. Are we cool with that? Awesome. The final one, so many regions I know, is outside of this cable or wire, whatever it was, cylinder. And again, we have magnetization is equal to 0 because again, it's just air. Do the same process again, and you find that H is equal to I on 2 pi s with no magnetic susceptibility, of course. And then from one of the other regions we did, we also know that B is equal to mu naught H. So therefore, in this region, Bs is equal to mu naught I on 2 pi s in the phi direction yet again. Cool. It's basically the same thing every single time, except in each region you have to remember the condition of whether or not the material in that region has some magnetic susceptibility, and then it's just the same process every time with just different variables. Part D is asking us it asks, how would the magnetic field for S bigger than 0 be affected if the cylinder were removed? And my answer was, or do you guys want to have a guess what the answer is? Yeah, so it doesn't change, and it's because the magnetic field around the wire is proportional to mu naught, so around the wire, S is bigger than C. It's proportional only to mu naught and I, and not to chi m. So no change. Cool.
You like calculate it with
Oh, yeah,
so I think would you actually think?
probably. I don't like Biosavar. I, for some reason, always was scared of it in 1B. So I think that trauma translated into EMAG. But if you like Biosavar, it's very useful. It is very useful.
Well, actually, no, you would just say that there's no magnetic susceptibility. But that is 0.
I guess. What do we use Biosavar as well for? It's for magnetic field, like near a wire. Yeah. And the wire can be some funky looking thing. Yes, I think you could, yes. You're such a mathematician, but yeah. Okay. Do we feel like taking a break, or should we just keep plowing through?
The one is chatting.
What do you guys feel like doing? What does that mean?
I need to chat.
Break? Yeah. I will say for the next 2 questions, I'm pretty sure they were Shushkov questions. I haven't seen Shushkov to talk about them. Alex said that the 3rd question was fine. And then in my last question, there's just some things that I needed to change. But they're just minor things, and we can talk through them. I also, wait, I should tell you guys what else Liz told me in the meeting we had today. Let me just remember them. Davide, what were they? I told them to you. Yes, I did. I literally got out of the meeting and then said everything. You're so lying. Okay, let me just, yeah, honestly. Okay, hang on. So Liz said, now I remember, Liz said that the best way to prepare for her half of the exam is to do the practice. Did I already say this? Yeah, I did.
Say it again.
Okay, she said the best way to practice for her half, because she hasn't written these past papers, the best way to practice for her half is to do the practice midterms. And I don't know if you were there for that lecture, but she said, you were there, I think. We need to know how to set up an integral.
Yeah.
Yes. And then Oleg section, one of the questions, he's not going to copy paste into the exam, but it's going to be similar. So it's probably going to be the circuit question, or if it's not the circuit question, I reckon it's going to be a toroid question.
Circuit question last year.
He's done a circuit question for like 2 years, right? Didn't we look at it and we saw he's done 2 before? Yeah. So I reckon he's going to do toroid. I also have seen 2 toroid questions in past papers, and one of them was like way back in 2015. And I don't know who took electromagnetism in 2015. Not even Liz or Peter know. And I asked them. Yeah, she did say that it was easier than the midterm, she feels like. But she also did say that like under exam pressure, like things could still go wrong. So
Yeah.
I mean, she saw
Maybe.
the results.
Yeah,
She's like, it's so that like in this language that needs to be all very. It's one at a time. See, the girl who looked at the exam, she's like, guys, did you enjoy my infinite Solomon question? And then she slowly like I think she realized that nobody like responded to that. And she was sad and people were
But yeah, hopefully it's okay. It's really disgusting that they put it on a Saturday.
Yeah.
That's really
Well,
filthy.
no, the real issue is that it's right.
That it's what?
That it's right.
And normally the physics ones are right at the end. Like my other physics one is right at the end. And it's not even like it's a big cohort either. Yeah. Yo, my goodness. I think Ari once tried to pull that card. I think it's the Sabbath card. I'm not joking. Yeah. I think he tried to pull that one time. Yeah. Yeah. Also, has anyone tried to email Oleg? No, okay. I tried to email him to get a thing set up, and I think I'm going to be able to get a meeting with him tomorrow over Zoom. So if anyone has any questions they want me to ask, I'm going to ask him about all his past paper questions.
Can you ask him if we're going to be provided with no materials for questions? Because I was doing.
What note integrals do you need for his ones?
I was going through some of his tutorial questions, and after he gets like an integral, like 1 on x squared plus y squared, x or whatever.
Yeah.
And he just goes, oh yeah, this is arctan,
Classic. Classic.
Yeah, I know that.
Yeah.
I can see that happening.
Obviously.
But
Duh.
I just asked him if there's learning.
Okay, cool.
Because Liz said it'd get constant.
Yeah. And also Liz today told me no Legendre polynomials, which probably means no multipole expansion. I kind of like multipole expansion. Anyway, should we get back into it? We've got 40 minutes and 2 questions left. Okay. Let's get into this. So, oh my gosh, I need to click my hip. Question 3. I'll probably also, this might actually be annoying. I might hold off on releasing the other past paper solutions I have until I talk to Shushkov tomorrow. So that I know that they're like at least the most correct I can get them. Awesome. Okay. Question 3. We have an alternating voltage source connected in series. Okay, so they set up a circuit basically, and then they ask us to derive an expression for the magnetic field of the conductor and hence the inductance. Let's do it. Okay. I'm gonna go super speedy. So this is the way I drew my thing. Alternating voltage, some circular inductor, and N is equal to 500 turns. And we have some circular resistor, my bad.
A circular resistor.
Oh yeah. Oh yeah. Oh my bad, yes, spherical. And I can't remember when this is useful, but it is eventually.
Is that the same as like a normal resistor?
A spherical resistor. I think it's just like I actually don't know what makes a resistor other than just it opposes current or slows the current down. Thanks for coming. Take some more chocolate, please. Awesome muesli bars. Okay. See ya. Say that one more time. I'm pretty sure. We'll find out, shall we? I can't remember.
It's just it's like saying there's 2 shells and the resistance is in the inside. So you have to calculate the volume. Or like
Maybe. I actually can't remember. Yeah. I'm looking at my diagrams and yeah. Oh, yeah. Oh, this took me forever to understand what was going on. Okay. I can't even remember what I read out for the first question, but oh yeah, B field of the inductor and inductance. We have the following. N is equal to 500. We have R, the inner radius is equal to 0.1 meters, and the R out is equal to 0.12 meters. To calculate magnetic field, I'm going to use good old Ampere's law, and that's written as this. Where's Are they looking in? B dot dl is equal to mu naught I enclosed. Because of symmetry, I can chuck that out the front, and that becomes a constant, and then I need to do the integral over dl, and because it's a circle, it just becomes 2 pi r, and this becomes mu naught I. This is a really big point. This came up in lectures, and we talked about it. Because we have n terms, we have to add an n here. Do you guys remember that? Okay, beautiful. Rearranging, we get b as a function of r is equal to mu naught n I on 2 pi r. I'm pretty sure this is even like a first year result. Awesome. To calculate the inductance, maybe we did this in our assignment, I honestly can't remember, is equal to n phi on I. To calculate phi, it's just this formula. It's the area integral of b dot dA. And I want to find that from r in to r out. And it's my b dot L dr, because my area integral is going to be some little radius multiplied by a length. Does that make sense? That's also, this is also kind of like constructing an integral. Also in the second question of the midterm, kind of same sort of vibes. You're looking at a little square on the outside of a sphere, but except that one is r d theta d phi. Different, but kind of the same idea of building the integral. When we do that, we get, plugging in the b that we got before, because of symmetry. You can take it out and make it a constant. That becomes I. This L is also a constant with respect to R, and this becomes 2 pi, and it ends up just being an integral from R in to R out of 1 on R. Doing that, I get mu naught NIL on 2 pi ln R out on R in. Another thing I noticed when I did this question is that this question is pretty similar to one of Shushkov's tutorial problems. So I think that like if you can just go through Shushkov's tutorial problems and like know roughly how to do them, you should be pretty okay for his part of the course. Because in another half of one of his past papers, he almost matched a tutorial problem exactly. So that's another little like hint, something that might be useful. Oh wait, multiply what by what? Yes, so we want to find the L, the inductance, and using the formula we had before, we need to multiply by n again. So we get mu naught n squared L 2 pi, and then this thing again. And I remember in lectures that we had this whole discussion of why it's n squared. I can't remember the reason, but I trust the math. Yeah. Yeah. I just trust the maths, honestly.
There was one L, there was one N that was coming from. Take out all, like take two loops together and take them out. That becomes your area, twice the area on the side. That was one of the ends.
I trust you. I trust you.
But yeah, the N times.
I still fight because you have phi going through n loops. Yeah, I do get that. Okay, cool. Oh, and then to finish this question, sub in the values, but I assume you guys can all do that. Part B, we want to find the electric field inside the resistor and the resistance. So dimension's a little bit different in this one. That's a 2. Oh no. R out 0.04 meters, and this thing, the resistivity, is equal to 100 ohms per meter, per centimeter, which is equal to 1 ohm per meter. Cool. Using Gauss's law this time, because we want an electric field, E dot dA is equal to Q enclosed on epsilon naught. Because of symmetry, I take this guy out, and then it's an area of a sphere because it's a spherical resistor. I get the surface area of a sphere, which is equal to Q enclosed on epsilon naught. This is where I do something a little bit not a little bit funky. I say that this is just equal to some constant. Because there are no free charges, because we're in a resistor, resistors only not oppose charge, they only slow it down. So we only have the charge traveling through the wire in our resistor. There are no free charges. So then I say that I can make that right-hand side a constant. If I divide by the 4 pi, which is also a constant, I'm going to get E times R squared is equal to another constant, which I'll still call C, and then I get E as a function, as a function of R is going to be my C over R squared. And C was Q on epsilon naught, 4 pi.
So that's just to make it look nicer for you?
Yeah, basically. Also, this is another thing Liz told me. You can also, instead of writing 1 or 4 pi epsilon naught all the time, just write K, which I like doing because, like, I don't want to use brain space remembering 1 or 4 pi epsilon naught. Filthy. Anyway. Continuing on, we also want to find the voltage in order to find the electric field later on, the resistance later on. So in order to do that, this guy again, and then when I do that, I get negative R in, R out, C R to the negative 2 dr. I'm just going to write the result of that because it's pretty easy to do. I'm going to get V R is equal to C 1 on R out minus 1 on R in. And then I want my value for C, and you'll see why later. So that's going to be a VR, and then this thing again, but with -1. Awesome. And then to find resistance, good old Ohm's law. To get resistance, and we can use this because it's a series circuit and there's only one resistor as well. So yeah, actually we can just regularly use Ohm's law. This. Awesome. And then because it's a spherical resistor, like Zale said earlier, we do need to consider the volume. This is also another super important equation that I found was helpful in solving a lot of the past paper problems. And then this one, resistivity, or sigma is equal to 1 on resistivity. Okay, using all that information, we have this integral, which is again super popular in Oleg's section. And then subbing in what we know, that becomes this. Plugging in that electric field we found before, I can take out my sigma because that's just a constant. In my electric field before, I had a voltage, so that's my V. I also had my 4 pi from before. My epsilon naught will go away, and I have my 1 on R out minus 1 on R in, and then that current is from R in to R out, and that's just with respect to dr. So I get, can I copy paste? Hang on one sec. From this line to this line, I substituted in the E that we got before. My C on my C thing. Sorry? So I is equal to Hang on.
You're
I'm
square
having
shifting into the R equals I.
Yes. So I'm using a combination of Ohm's law, but in Ohm's law I have a current, and instead of just having a regular linear current, I have a volume current, which I use this for. And then this is the same as this here. So I essentially have, I start with I, actually hang on, I start with I, and then I can re-represent, oopsies. Hang
You're
on.
kind of making a jump. Like you haven't solved
I am, hang on. Let me see if I can explain this. What was I thinking? Oh, let me, I missed a step, hang on. Let me add a step in here. If I do the straight substitution into this integral, I get this. I get sigma, which we hopefully agree is a constant, is, I don't actually even know if this will be helpful to what I'm trying to explain. There's a minus sign in there. R in 4 pi r squared dr. That's the straight substitution. Can't zoom out anymore. So we end up getting to this, and then I, in my working out, just say make sigma equal to this because we get given the value of rho, and then sub in all the other components, and then you'll find your final current. So that's basically how you do it. Just find the expression and then just plug in some numbers and write down the answer. Now we get to the fun stuff, and this is part C. We need to use Kirchhoff's laws to get a relationship between I and V. So basically the assignment question. What I do is I can't remember, I think it's the voltage law. The sum of the voltage is equal to the sum of the voltages across the loop. So it's like this. And then my V in, they tell you, is sinusoidal. I'm pretty sure they even explicitly say is this. My voltage of an inductor is L di dt, and the voltage across a resistor is IR. Okay. This is a part where I completely disregard the physics and I'm just looking at the maths. So this is a non-homogeneous differential equation. Hopefully from first year maths, you know that in order to solve this, you need to first solve the homogeneous equation, which is just the differential side when it's equal to 0. So in order to get it into a nicer form, I'm going to do this plus I on L, no, R on L is equal to 0. In order to find the solutions to this, I'm just going to find eigenvalues first. So writing the characteristic equation, I get this, and I get my two eigenvalues are lambda and negative R on L. Another thing to remember is the form of the differential equations for this kind of, no, the form of the solution to the differential equation for different differential equations. So for this specific one, it's going to be I is equal to AE to the negative R on LT. And you can be confident with this one because in the notes, if you remember, it specifically says that for an RL circuit, which is what this is, the kappa factor is R on L. So that means we're on the right track. Now we need to find the particular solution. So I basically just say, because I know that my input voltage is oscillating, my current is also going to be oscillating. So I say, I just don't know how. So I say, let my I equal to some I naught cos omega t plus I1 sine omega t. And then I find the derivative. And then if I do it correctly, I hopefully get this. And then I'm not going to write the whole thing out, but essentially you just chuck it back into the equation. the differential equation, and you get this. You get V cos omega t is equal to Li1 omega plus L1 I1 omega plus I naught R cos omega t plus Ri1 minus Li naught omega sine omega t. And hopefully this is pretty similar to what you guys did in the assignment. And if not, that's going to make me stressed because this is what I did in the assignment. Anyway, now I want to compare my coefficients, and I see that, oh, let me get rid of that. Comparing coefficients. And I have that Li1 omega plus I naught R is equal to V naught, and I have Ri1 minus Li naught omega is equal to 0. From this one, I get that I1 is equal to L omega on R I naught. And I'll just label these 1 and 2 to make it easy. And then I'm going to do 2 into 1. And from that, I get, do you guys want me to write everything step by step or just the answer? Yeah. Are you guys actually going to follow if I chuck everything in and then do simplification? Maybe not. So essentially from doing this, you get I naught is equal to V naught R on L squared omega squared plus R squared. And then by subbing this one in to 1, you will get, so this is just solving simultaneous equations, you get L omega V naught on L squared omega squared plus R squared. And then that means that we can plug those values back into our ansatz or our guess, or whatever you want to call it. And we will get that IT is equal to AE to the negative R on L plus V naught R L omega squared plus R squared. And then I'm going to do this. Uh-oh. So this is my homogeneous solution, and this is my non-homogeneous solution. And we know that the general solution is just the sum of both of them, or any linear combination of any of the solutions. Sweet. Cool, cool, cool. And then that's the end of that question. The next part asks to find the frequency where the voltage across the resistor and the inductor is half of the input voltage. I reckon, do you guys just want to know how to do this question? And because it's pretty simple, it's just a lot of algebra, and then we can have the last 20 minutes doing the very final question. Okay, good, 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 good. There's just one thing I also wanted to point out that might be wrong with my solution, but I will ask Oleg tomorrow. Or maybe someone here can answer it, because that would be really helpful. To find the frequency where it's half the voltage, I first want to find the steady state current, just because like we don't really care about the transient stuff because it's always changing or decaying or whatever. What are the bets he puts like a dampening constant in the final? That could actually, ooh, okay. Because that's exactly what like the assignment question was, but it's now just with dampening. And we talked about dampening. Anyway, back to the question. Steady state current. The steady state current literally just means like the part of the general solution that isn't decaying. So it's just going to be the cos and sine terms. I actually think I miswrote it up here. I did miswrite it up here. The constant in front of sine is L omega. I just got too excited. Oh, squared and plus R squared. So I just want this to be my steady state solution because everything else is decaying. Okay. So I have my steady state solution is going to be this, V naught R. Okay, cool. And then if do I need to do that step? Yeah, I'll do that step actually because it's kind of important. If I factorize this as much as I can, I'm going to take, the denominator is the same, so they're fine. I'll take the V naught out from the top, and then I'll leave this as an R cos omega t, and I'll leave this as an L omega sine omega t. I'm now going to use the trig identity where I turn the sine into the cos. The reason why I want to get into the cos is because my voltage input is also in terms of cos. So if I do that, I'm going to get V naught on that's supposed to be squared, cos omega t minus phi. And this is actually a really good thing. If anyone has ever done a lec, you'll know that the current either always lags or leads the voltage. And what that means is that the current will always be the same as the voltage, or the same form as the voltage. The constants might be different, except there's this constant here, which means that if you read it with an oscilloscope, you'll see that the voltage and the current are not exactly in line. They're out of phase by this phase translation. And then this is also something in the notes, but if you're an electrical engineer, then you'll just know what it is. To find this phi, we want to take the arctan of the imaginary component of the impedance over the real part of the impedance. I can't remember if this was used in the assignment or not. I think it was, because we had to find phi, right? But I can't remember how we found it. Anyway, by plugging in these values we get, or these variables, we get this. Cool, cool, cool. Awesome, and then that means we have, hang on, our phi. You can then substitute that back into our voltage we had before to find VR. I'll just write down the steps because we are running out of time and I want to do this last question. We want to find VR by plugging phi in. That's bad English, but you guys know what I mean. And then you want to set the voltage across R to be equal to half of V naught. And then you essentially just solve for the omegas that you're going to have in there. This is where it gets a little bit iffy for me. When I did it, I got two solutions. I got omega is equal to √3. This would be R on L. But I also get, I'm pretty sure, yeah, I get 1 on √3 R on L. So that means that there's two frequencies where the voltage across the resistor and the inductor is half. But I can't explain it. Can anyone else explain that? What's arctan finding? A phi angle. Yeah, we only want one phi angle. I also remember in the assignment, I got 2 resonant frequencies. The only thing is this is not talking about resonance, but it's like kind of related to resonance just because, yeah. Hang on, let me just look back at the question because in the assignment it said frequencies. In here it says find the frequency at which the voltage drops. So one of these isn't legit, but I can't tell you which one. So I'm gonna have to ask Shushkov. I got 2 answers. One second, let me just look at my calcs. So I used Ohm's law, V equals IR, and then I substituted in, I rewrote my VR by plugging in my phi, and then I did this, and then I found omega that way, and then I did the exact same thing but for the inductor. So I used VL is equal to, I plugged it into this equation, di dt, And then I get an equation for VL, and then I set that to be this, and then I find another omega.
You got a solution.
Yes.
Isn't it also when they're both
The thing is, though, by assuming that the voltage drop across one is half the input voltage, that automatically assumes that the voltage drop across the other is V naught on 2 because of Kirchhoff voltage law. The sum of the voltage in the loop is just is equal to the input voltage. So assuming one assumes the other at the exact same time. So I don't think that's a problem. I have to ask Shushkov. I don't know. I really don't know. I'm sorry. Are we good to move on though? Cool. I will, when I ask Shushkov and annotate my answers, I'll put little comments in my notes or in my solutions. But that was just the problem that I had with that one. Let's speed run through this last question. It's talking about polarization. So do you guys all have access to it? Because I don't want to waste time reading it out. But essentially you have two polarized things, two polarized waves, one traveling along the x-axis and one at 45 degrees. And I think the first question is asking us to write equations for them. The first one is going to be this. K is also a wave number. Just remember that. I don't actually even know what a wave number is, to be honest. I just accept it, which might not be a good thing, but it's okay. If the maths works, it works. Do you guys know what a wave number is, like in real life? No? Yeah, that's what I think it is, but I don't think it has any physical manifestation. Anyway. Sorry. Oh yeah. Another fun little thing, which I actually had very little recollection of until I looked back at the lecture notes, is that K, and this is a first year thing as well, is equal to 2 pi on lambda. And lambda, or lambda in a medium is equal to, oh, thank goodness. Oh, thank goodness. Lambda in some other medium is equal to lambda naught, which is the lambda in air, over that constant in the medium. What's that called? Refractive index. I was going to say Snell's law. That's right. Okay. Cool. And then K2, kind of similar thing. Oh, actually, let me just rewrite that. Because we have this, we can rewrite K1 as K1 is equal to 2 pi. And then if I plug in lambda, I'm going to get N1 on lambda naught. So that becomes 2 pi N1 on lambda naught times X in the X direction. K2, really similar. We find K2 using this as well. And because we're in the same medium, it's still going to be in terms of N1. But this time we need to take into consideration the 45-degree angle. Cool. So that's question 1. Question, or part B, says it wants us to find the combined electric field in Euler's form. So we know that wave 1 is polarized in the y direction and it's traveling along x. This means that there are only components in the y direction, but it's in terms of x. So another way of writing that out mathematically is by saying this. This E naught, they tell you, is the amplitude of the waves in the beginning of the question. I'm just going to write K1 because I don't want to write out the whole fraction. So it's in the direction of y, but it's in terms of x. In the direction of y. Awesome. He wanted it in Euler form, so chucking it in Euler form, we just get this.
That looks like an equation sort of thing.
The Euler form? Yeah. Uh-oh.
So just like the wave number vector or whatever minus omega t.
Yeah, it's the argument of the cos raised to the power of I plus e to the negative I times that argument. Again, this is in the y direction. Cool. This second part I was kind of stuck on for a while. It asks you for the one for E2 as well. So it also tells you that it's circularly polarized, and for some reason I was stuck on that forever. I'm just going to write out the final Euler form because it's the same thing every time. Writing out Euler's form, you get e to the I k2 x minus omega t plus e to the negative I kx. That's k2x minus omega t. That's in the x direction, and then we need to add the corresponding y direction. And it's the exact same thing, except when we convert sine, we have to chuck a 2i down here. And then this is a y minus wt minus here, e to the negative I k2 y minus omega t. That's in the y direction.
And they're 1 on 2 y.
Yeah, so to convert from a sine to the Euler form, it's 1 on 2i and then these exponents. And then the combined electric field, just add them up. Literally just add them up. I'll write that here. E total is equal to E1. So it's circular, hang on, whoa. Let me read the question. I don't think Alex flagged that. So wait, hang on. The second wave is right-hand circularly polarized. Oh, remember it also depends like which way you look at it as well. Remember that thing? Because if you look at a circularly polarized thing from the side, it just looks like it's oscillating up and down. But if you look at it face on, it looks like a circle or like a thing coming out like that.
Down the XY plane, you're going to see it.
Wait, down the XY plane as in like...
You're going to see it going Z and X/Y.
Oh, you'll see it in all three directions.
No.
If you're looking at it from the Y plane, you're looking at the Z plane from being on the Y plane. Is there like whiteboard markers or something? You probably won't see green. Hang on. I don't know if you'll be able to see this. Okay, that's also wrong. Oh my gosh. So this is Y, this is X, and this is Z. And it said circularly polarized, right-hand circularly polarized as well. So I really want to say that that means that. Am I okay? Oh my gosh. That's a Z. Right-hand circularly polarized, I really want to say, I actually don't know what that means. Yeah.
Circularly polarized, and you have rotating about the direction of travel. So they're passing through.
They have some Z component. That means they also have an X component and a Y component. That's really yucky.
I just said like I chose Y. But
if it's right-hand circularly polarized and it no, but we know it's moving in.
There was also another paper where he like
another one.
The circularly polarized form.
I guess I'll have to ask, because then this is what I use for the whole part of the question. Let's just assume this, and then I'll show you how to answer every single part. And then when I ask him tomorrow, I'll tell you guys. That's so annoying. That's okay. Combined electric field, sum the electric fields. The very last question is determine an expression for the energy density at x equals 0 and sketch the result. Okay, this is the part. Alex said that he didn't check this super thoroughly, but the method seemed correct. This is also the past paper that Alex had to sit as well. Fun little fact. He said the first question was heinous. He left that as a little cute little note. Okay, so expression for energy density. Let's go. This is actually like kind of easy-ish. From lectures, as you see, energy density is equal to epsilon naught on 2 times this. At x equals 0, E total is going to be some disgusting long equation. Let's not worry about it because we have like 2 minutes left. It'll be in my solutions that I put up there, so it's okay. You find whatever that is out, and then you have to square it. When I did this question initially, it asked us earlier to put in Euler form, and then it asks us in the next question to square it. I feel like it's a lot easier to square trig identities than it is to square a sum of exponentials. So I converted back into trig. I also asked Alex, like, what is even the point of this? And he goes, it's a lot easier to see interference effects when you use Euler form. So that's a fun little fact, but I didn't use Euler form when I squared it. So I just squared my trig integrals. And when I did that, I get this expression. Squared is equal to E naught squared. And remember, I'm taking a vector equation and I'm finding its magnitude. So you're just squaring this, you're squaring each component and then you're summing. That's that. And then I get another one here. And then I actually get this one. And then I get a sine squared. K2y minus omega t. Okay, cool. And then it wants you to find the average energy. So we take the average of this. And we literally did this in the last shoot. So a really easy way of doing this is we just start taking averages of each of these components individually. So the time average of cos squared is just going to be 1/2. Time average of E naught squared, it's just a constant, so it's E naught squared. Time average, oh, that's also a squared, sorry. Time average of cos squared again is, what have I done? That should not be there. Time average of this one is 1/2 E naught squared, and then time average of a sine squared is still 1/2. So I get plus 1/4 E naught squared. If I sum those up, I get 7/8 E naught squared. And to me, that makes sense because, actually, no, that doesn't make sense to me because I feel like the energy density should be bigger than 1. Because you have 2. I am. No. 1 second. Sorry, yes, my bad. I did not do that in my notes. That's where that 1/2 came from. That's a 4, and that's an 8. But that does get you to 7/8. I think that the energy density needs to be bigger than 1, though, because you have 2 energies going in the x direction.